are in listen-only mode.
Hi everyone, welcome to today's webinar, Mercury Spills and How You Can Avoid Them. My name's James and I'll be your moderator for today's event. So before we dive into the presentation and turn things over to our speaker, I'd like to give you a brief overview on what this event really entails, and we'll walk through some housekeeping items too briefly. So we'll start with a slideshow presentation providing some background on Mercury, where it can be found, and then we'll move into some strategies for measuring vapor levels and remediation techniques. Again, our speaker will address the agenda in more detail, but that's what you can expect from a content perspective. At the end of the presentation, our speaker will walk through some real-world case studies to drive some of these lessons home and give you some tangible examples. Following the presentation, there will be an open Q&A period. You can ask questions anytime throughout the webinar, which is encouraged, by typing them into the questions pane over on the right-hand side of your screen. Please note that everyone's microphones will be turned off for the entirety of the webinar, but if you do have a question or a technical issue comes up, once again you can use that questions pane to communicate, and I'll address that for you. Finally, please keep in mind you will receive a copy of the slide deck and the recording tomorrow, so all of the materials that are presented today will be in your inbox tomorrow. I'm pleased to introduce our speaker today, Ryan Miller. Ryan is an environmental engineer at Triumvirate Environmental, where he's conducted numerous environmental engineering projects and remedial response actions. This includes tank removals and closure reports, lab and facility decontaminations, hazardous building materials identification, and building demolition oversight. Mr. Miller has also carried out engineering consulting services, and this includes building material inspections, namely Mercury, and emergency spill response work throughout his career. And with that, I will turn the microphone over to Ryan. Hey, Ryan.
Hey, welcome everybody. Let's get started. Just go through the agenda about what we're going to go through in this webinar. We'll start out with a little bit of background on Mercury, and then we'll move into mercury vapor measurement and the regulations, followed by mercury spill response, and then I'll give some real-world case studies. We'll end with a summary of everything and a Q&A. So with that, what is mercury? Mercury is a naturally occurring element that in its pure form is a liquid that is readily volatilized. Exposure at high levels can harm the brain, heart, kidneys, lungs, and immune system. And mercury vapor is colorless and odorless. So the consumption of fish is by far the most significant source of ingestion-related mercury exposure in humans and animals. Plants and livestock can also contain mercury due to bioconcentration from mercury ingestion. And exposure to mercury can occur from breathing contaminated air and from improper use or disposal of mercury and mercury-containing products. Mercury, especially organomercury, such as methylmercury, is readily absorbed through direct contact with bare or insufficiently protected skin. So where can it be found? It's commonly found in thermometers, barometers, manometers, light bulbs, thermostats, and coal and other rocks in the natural environment. Coal-burning power plants are the largest human-caused source of mercury emissions to the air in the United States. The mercury in the air eventually settles into water and onto the land, where it can build up in fish, shellfish, and animals that eat the fish, and even humans. Also in the U.S., mercury compounds are manufactured in small amounts for specialty use, which can add to those air emissions. This is just an illustration of that mercury cycle. Mercury cycles from the Earth to the atmosphere, to the oceans, and back to the Earth. In the ocean, that mercury is converted to monomethylmercury, which is a neurotoxin that moves up the food chain and becomes highly concentrated in tuna, swordfish, and other fish that people eat. Wastewater can also contribute to this cycle. In the greater Boston area, the Massachusetts Water Resource Authority closely monitors that type of contamination. Why is mercury used? Mercury has a unique combination of physical properties. It has a low melting point of -38 degrees Fahrenheit. Now lead, for example, as another metal, is 622 degrees Fahrenheit. So in its natural state, mercury is a liquid at standard temperature and pressure. It also has a low boiling point of 674 degrees Fahrenheit compared to lead, which is 3,182. And another unique property is that it has a uniform volume expansion over the entire range of temperatures in its liquid state and high surface tension. And it does not wet glass. So these properties make it useful in the measurement of temperature. That's why it's in thermometers, as well as pressure, and that's why it's used in barometers and manometers. Mercury also has a high electrical conductivity, which has led to its use in sealed electric switches and relays, industrial power, fluorescent mercury vapor lamps, mercury cell batteries, and as moving cathodes and large-scale production of chlorine and caustic soda. So where can it be found? Devices commonly found in facilities are barometers, fluorescent bulbs, mercury thermometers, clinical manometers, sphygmomanometers, and thermostats. Breaking these mercury-containing products or improper disposal, improper treatment, and improper cleanup of mercury spills can release the mercury into the environment and cause a health hazard to the workers. One important thing to note here is that containerized mercury is commonly disposed of as universal waste. Once these devices are broken or the mercury is no longer contained in the device, it poses a hazard to human health and the environment and is now considered a RCRA waste, which is a Resource Conservation and Recovery Act listed hazardous waste, which is different than disposing of it as a universal waste and can be more costly and more dangerous. So with that, a quick poll question for everybody. Are you storing old, obsolete, or unused mercury-containing devices? Give a second to answer and share that answer in a moment.
All right, so it looks like most of our audience has answered. I'm going to close that poll now. And 37% say yes. They are storing old, obsolete, or unused mercury-containing devices, and another 63% say no.
That's good. So if you do have these devices that are known and they are obsolete, old, or unused, disposing of these materials now before they cause a spill or the mercury to be released should be considered. Mercury can also be found in plumbing. A lot of old buildings where laboratory settings or otherwise, mercury is poured into the drains and it can remain in the plumbing indefinitely until it is physically removed or the plumbing is replaced. So this happens as liquid enters the plumbing system carrying organic liquid waste, bacteria, and mercury. The elemental mercury and mercury salts are metabolized by the bacteria. Chlorides are oxidized to chlorates and mercuric ions are released. Mercuric ions combined with methyl ions, generating methylmercury and dimethylmercury, are then adsorbed and bioaccumulated in the organic biomass. So what this means is if you have a mercury-containing waste poured down the drain, you might not see elemental mercury, but that methylmercury and dimethylmercury are actually adsorbed to the organic biomass within the system. So this can release vapors through the piping and out the drains and potentially expose employees at those sinks where the mercury was disposed. Mercury is commonly found in laboratory sinks, and in most cases, removing the trap will remove the source. Triumvirate also utilizes a camera snake to investigate further with mercury vapor readings as well, and I'll get into how we measure those readings shortly. But like I said, if mercury's heavy, it'll settle into those traps, and if those traps are removed, you're likely going to be able to remove the source quickly. There's various reasons why mercury can be in soil. This illustration was an old laboratory waste pipe that was capped within the building, and ran to the sewer. It was unknown that that cap remained, or the pipe remained after it was capped. And when the pipe was pulled, elemental mercury was released onto the soil. So to remediate something like this, the soil had to be excavated and containerized. Headspace readings of the soil and laboratory analytical were collected to close the remediation. In Massachusetts, the method 3 upper concentration limit, UCL, for groundwater and soil is 200 micrograms per liter and 300 micrograms per gram. Now these concentrations vary per state, and in most states they actually vary with depth. So in regards to human health and potential exposure, usually the top layer of soil has the higher concentration limit, and that as limits increase as depth increases, and this is realizing that mercury is naturally found in soil, so it's just taking that into consideration. All right, so moving on to mercury vapor measurement and regulations. We'll touch on how mercury is measured and what regulatory guidance we have to follow. Mercury vapor measurement. There are various methods used to detect and quantify mercury vapors in air. Vapor detection limits vary significantly, and regulations and guidance concentrations can be confusing because they're presented in milligrams per cubic meter, micrograms per cubic meter, or nanograms per cubic meter. So whenever dealing with mercury vapor concentrations, as well as any other analytical, it's important to really look at the units. Mercury vapor measurement. Now that we know where mercury contamination can be found, how do we quantify it? Well, we can use some of these tools shown here. Mercury vapor meters are the easiest method for real-time results. What we're illustrating here is a Jerome J505, a Jerome 431X, an X-ray fluorescent analyzer, or an XRF, a Draeger, and a Lumex. These samples can be analyzed at a laboratory also. If you collect groundwater or wastewater, soil, even wipe samples of surfaces, you can submit those for laboratory analytical and get a mercury concentration. This table, which I kept the units in milligrams per cubic meter to keep it simple, to really illustrate the point of the detection limits for each one of these. So Draeger tubes have a detection limit of 0.05 milligrams per cubic meter, whereas something like the Jerome J505 can go down to 0.00005 milligrams per cubic meter. The EPA method 6009 goes to 0.002 milligrams per cubic meter. That's using Draeger tubes. And the Lumex has the same detection limit as the Jerome. The Jerome, older Jerome 431X has a concentration detection limit of 0.003, and it has a plus or minus an error of 0.003. So it's tough to actually get 0 with the Jerome 431X. Now Triumvirate utilizes the Jerome J505 for most mercury vapor monitoring activities, and that is due to the low detection limit, and also because some other meters actually have known interferences. So there's potential interferences to the Jerome 431X mercury vapor analyzer and have been identified and listed in the manufacturer's owner's manual. Erroneously high readings can sometimes occur with the presence of hydrocarbons, high levels of carbon monoxide, carbon dioxide, sulfur dioxide, water vapor condensation, chlorine and ammonia, nitrogen dioxide, and hydrogen sulfide, and mercaptans. These interferences are common to the natural environment in areas where mercury remediation is usually necessary, such as laboratory waste piping, chemical laboratories, mechanical aerators, etc. So that is why Triumvirate uses the J505 for the Jerome, because there are no known interferences to that or the Lumex meters. So, regulations and guidance to all of these detection limits. OSHA has established a PEL as a ceiling value of 0.1 milligram per cubic meter. This is the only legally enforceable federal U.S. standard for mercury. NIOSH set an REL of 0.05 milligrams per cubic meter as a 10-hour time-weighted average. The ACGIH, which is the American Conference of Governmental and Industrial Hygienists, then came out with their study and did a recommended, the most recent occupational exposure standard as a threshold limit value time-weighted average of 0.025 milligrams per cubic meter, which you'll note is half of the REL. Then more studies were done by the Agency for Toxic Substances and Disease Registry, or the ATSDR, and they recommend risk managers isolate humans from mercury spills when a concentration level of 0.01 milligrams per cubic meter is detected. The ATSDR also came up with this list of specific concentrations for when mercury is found in specific scenarios. The cleanup guidance states that residential occupancy or the immunocompromised, which does include hospitals, follow a less than 0.001 milligram per cubic meter concentration. The acceptable personal effects level, which would be if somebody were to have a spill that contaminated their clothes or their boots or a backpack or anything of that nature, that the concentration of that item be less than 0.01 milligram per cubic meter. Residential isolation is recommended when concentrations are greater than 0.01 milligram per cubic meter, and that is to say if a thermometer is broken in somebody's home, they should isolate the area from those residents at that concentration, so keep them out. And then reoccupancy after the spill, and this is for a commercial setting or a laboratory setting, research setting. They recommend a concentration of 0.003 milligrams per cubic meter. And they even set a level for an occupational setting where mercury is handled at 0.025 milligrams per cubic meter. So that's a lot to take in, but these are recommended values that we like to follow at Triumvirate because they're the most stringent, and there's a lot of study to back these levels up for human health and safety. So now that we know how to detect mercury, what levels we need to get it down to, we can talk about mercury spill response. The most important thing after a spill is worker health and safety and prevention of further contamination into the environment. So spills within a facility can pose a threat to worker health and safety and to building occupants. If they're cleaned up improperly with improper PPE, sources of cross-contamination by spreading the mercury as opposed to actually cleaning it up, remaining hot spots, say an area isn't clean or you get mercury that has penetrated into an area that you didn't know it could, maybe between floor tiles or behind cove base or even onto porous materials. That's likely during a cleanup if it's handled improperly. And improper waste disposal. Those are all things that can lead to exposure, worker health and safety issues, and environmental compliance issues. So Triumvirate's mercury spill response. In emergency response situations, self-contained breathing apparatus, SCBA, is used to enter the isolated area where the spill occurred and determine mercury vapor levels. Once those levels are determined, then the appropriate level of PPE is determined, whether that remains in a SCBA or you can downgrade to a full-face respirator with mercury vapor cartridges. That determination is made, and then the decontamination is preferred. is performed. So every response is unique, but some basic concepts for mercury remediation are universal. These universal concepts include the following, and that's isolate the area and prevent access from anybody who is not involved in the cleanup, setting up zones, and that's the hot zone, the decontamination zone, removing visible mercury, and that leads into don't cross-contaminate. So one of the biggest things when mercury is spilled is that beads can go very far, and it can be contamination in areas where you wouldn't expect it. So things like the vapor monitors and visible mercury and just a thorough inspection prior to entering that hot zone is going to really affect your cleanup outcome. Cross-contamination is one of the biggest things in a mercury cleanup. It's very easy to track. And then once that's determined and all visible mercury is removed, we select a grid pattern for screening, and that's setting up a 1x1 square and getting a concentration for that area to determine if there are any hot spots or potential sources of mercury in that space. And once that's done and we remediate to the appropriate cleanup standards, all the materials are properly disposed of. And in some instances, this process can take many hours, and sometimes it can take days. It really depends on the amount of mercury released and the area where the release occurred, and also the materials that are affected by the release, porous versus non-porous, and also the ventilation in the area. All of those things can determine how quickly that mercury and all the mercury vapor is remediated. So mercury cleanup products and equipment, these are common products and they're commonly used at Triumvirate. Triumvirate utilizes multiple mercury cleanup products to effectively eliminate mercury vapor releases, including the Mercury Vacuum, which is shown on the far right, and Mercury Amalgamation and Mercury Vapor Adsorption products, which are shown in the middle. And I will talk about those in detail right now and how they work. So first I want to talk about the Mercury Vacuum. A Mercury Vacuum is specifically designed to collect and retain liquid mercury in the centrifugal droplet separator for future disposal. It has a 4-stage filter, internal filter system consisting of an internal HEPA and activated carbon filters and a diffuser that capture 99.97% of particles down to 0.3 microns in size, which safely eliminates mercury vapor. I have a video on the next slide that I'll show of the Mercury Vacuum in use. We'll touch on that in a second. Next step for a cleanup would involve mercury amalgamation powder. The mercury amalgamation powder reacts with elemental mercury to convert it to mercury amalgam. And this helps eliminate the volatilization of mercury vapor. And it also is more readily collected when it is amalgamized. It turns gummy and almost like a paste. Instead of chasing around beads, you just have to clean up that paste and that powder, and it comes up a lot easier. And then the next step would be the application of mercury vapor adsorption powder. And this powder consists mainly of granular activated carbon, and the granular activated carbon demonstrates a high mercury absorption property, which will adhere mercury ions. So after the removal of the elemental mercury, the mercury vapor adsorption powder is applied to the spill area and ideally left for some time, maybe overnight, which will completely suppress any mercury vapor. So this is the centrifugal trap of the Mercury Vacuum. And as you can see, the process has been going for a while, and mercury is separated out into this trap, and any sort of dust or other debris isn't heavy enough to be collected in here, and it goes through the hose into the vacuum where it's collected in a bag and disposed of accordingly. And I'll just show this. So as you can see, we have a triumvirate employee using the vacuum. Up here in the corner, he's working his way to where the spill occurred. The cleanup started down this way, and he's working his way up to the source so we don't cross-contaminate. And you can see the beads that are being removed at that time. And judging from how much mercury was collected in that trap, I estimated it was around 250 milliliters of mercury that was cleaned up that day. So once that's collected in that trap, it can be removed from the vacuum, sealed, and it's containerized and safe for disposal. So with that, we'll talk about waste disposal. The most common disposal method for elemental mercury is mercury retort. Solid and liquid-bearing wastes are put through a controlled high vacuum retort system that recycles the mercury. And the mercury can be recycled up to 99.99995% purity, which can be used on a wide variety of applications. These applications include switch, semiconductor, fluorescent, light, and dental amalgam manufacturers, as well as for research laboratories or chlorine caustic soda production. So after triumvirate is done with a mercury cleanup for a client, we provide a remediation report, which includes background information, summary of cleaning activities, mercury screening levels and photographs, recommendations and conclusions, and disposal documentation. We provide the reports in electronic format unless otherwise requested. So that is mercury spill response in a nutshell. And with that, we'll move into some case studies, which are real-world spills and scenarios where these ideas and concepts and regulations had to be implied. So this is a mercury vapor turbine. Mercury vapor turbine is a form of heat engine that uses mercury to drive the thermal cycle. Mercury vapor turbines have been used in conjunction with steam turbines to generate electricity. The mercury cycle offered an efficiency increase with the fact that the complete cycle can be worked over a very wide range of temperatures without employing any abnormal pressure. The exhaust from the mercury turbine is used to raise steam for the steam turbine. That's why mercury was used in these big units. Power plants that use this include plants in Hartford, Connecticut, Kearney, New Jersey, and Portsmouth, New Hampshire. Case study is about a power plant, none of the ones that I mentioned, where mercury was released. So demolition and removal of equipment within the power plant was underway. During that process, elemental mercury was identified on the floor and subsequently identified throughout the area. What happened was the mercury was released from the mercury vapor turbine circulation system piping and onto the floor, walls, and even asbestos thermal sealant insulation that was being removed during asbestos abatement. So initial air screening was performed, and the air inside the area of the release and site boundaries were established, and it was determined that the plant had to be evacuated. Equipment, debris, worker clothing, tools, and anything in the vicinity of the release had to be assessed for visible mercury in the presence of mercury vapor. Segregation of contaminated versus clean materials was conducted, and preferential migration pathways were assessed, including the contractor vehicles, waste containers, drains, bags of asbestos, and stockpiled scrap were all screened. Everything was assessed, segregated, and managed accordingly. We then set out a contamination grid. This is an example of that grid that was designed in AutoCAD that illustrates where potential contamination still existed after the initial cleaning. So this grid was set up to determine where maybe pore space was affected, since it was a concrete floor. And this gave us a really good idea of where cleaning had to continue and where we could clear areas from that cleaning. The cleanup involved equipment segregation first of all, and after that, the vacuuming of dust and debris was conducted with the Mercury Vacuum, and the areas were screened. Areas below the action level were excluded from further decontamination, covered and secured from disturbance from any entry by workers and visitors. And areas were evaluated, and concentrations of mercury vapor were washed with mercury amalgamation powder. That process was repeated until all of the screening results were below the action level. Once we got everything below the action level, we did a NIOSH 6009 method for determining if re-entry was achievable. And we included a background sample and trip blank for quality assurance and quality control purposes. And the mercury results were reviewed and found to be below the action level, and the area was released for normal occupancy. And after the cleanup process, we provided a project summary report and documented a detailed description of remedial activities and all supporting information. So this is another case study of mercury that was found in a hospital, and you could probably multiply this 10 times over, because hospitals still seem to contain a lot of sphygmomanometers, and those are used to measure blood pressure. A lot of hospitals still contain mercury devices, including these, and we have to respond to spills in these cases. So when this happens, we evaluate the area and limit access. We remove visible mercury without tracking or cross-contaminating. Screen the area for mercury vapor concentration levels and identify hotspots and potential sources of the mercury. Set up zones, including a decontamination area, and begin decontamination activities. And it's important to note that in the hospital, we like to obtain mercury vapor clearance levels of 0.001 milligrams per cubic meter throughout the area, since there are immunocompromised individuals in that area. Then we collect all remediation waste for proper storage and disposal. Something to note here is floor tiles had to be removed along with cove-based molding, and things like patient beds and sinks and everything around the area has to be thoroughly screened to make sure that nobody is going to be contacting this material or exposed to it. Another common source for a mercury spill is old manometers. A lot of universities still have these as a teaching tool, but those teaching tools often lead to a more of a headache with a mercury spill. And in this case, it was a very large manometer, as you can see from the photo. And what we had to do was limit access to the area, screen for mercury vapor concentration levels, set up our zones, including a decontamination area, and begin decontamination activities. We removed visible mercury without tracking or cross-contaminating, identified the hotspots and potential sources of mercury. In this case, the permeated concrete surface and porous surface created a large area for the mercury to fall into cracks and holes. As you can see from that photo on the right, it was tough to identify where mercury could have been. So that's why it's important to have meters that are capable of directing that sort of cleanup. And we were able to vacuum and clean the area multiple times to obtain mercury vapor clearance level of 0.003 milligrams per cubic meter throughout the area, and also applied the mercury adsorbent powder and mercury vapor absorbent to make sure that those levels were clear for reoccupancy. And after that, we collect all remediation waste for proper storage and disposal. So I touched on mercury and lab piping earlier. I can get into a little bit more specifics. It's commonly found in areas where mercury is used for research, and also it can be found in areas where mercury-containing compounds, such as thimerosal, can be used as a preservative and inadvertently poured down the drain. So when it is identified either by laboratory analytical of wastewater, or it's identified with a mercury vapor meter, the typical remediation process is to remove each sink trap, collect the contents, and screen those contents. Traps that exhibit detections are removed and containerized for disposal along with the trap contents. And then remaining laboratory waste piping is screened, and any piping with detections is cut and containerized for proper disposal. All piping is removed until there is no detections on the drone. This particular pipe in the photograph had to be removed all the way to the vertical pipe before no detections were found, which is also common, and that's a successful way to remove mercury in lab piping. So after those case studies, I just have a brief summary of everything, and then we'll move into a Q&A. So to summarize, mercury devices can be removed or disposed of before a spill happens. Devices containing mercury are most likely able to be disposed of as universal waste, and it's better to get rid of them if they're not being used before a spill happens, because mercury remediation is costly and time-consuming, and if something is spilled, improper cleanup can lead to worker exposure and further contamination of the environment. And lastly, Triumvirate is here to help. We can help manage those devices, dispose of those devices, and we're available for emergency response. For those who currently use Triumvirate services, we can set up an ER agreement to respond to emergency spill. For more with that, you can contact your account manager if you're a client. Any questions?
Great, thanks, Ryan. I think that really kicked off a great Q&A where we're seeing some questions come in already. I know this is an important topic for many in various industries, and you mentioned a few throughout your presentation. So at this point, I want to encourage everyone who has a question, we've got some time here, to type one into the questions pane on that right-hand side of your screen, and we'll get those over to Ryan. So instead of using the chat hand, just type that message into the questions box. So Ryan, to start, one question gets back to the ATSDRs and those sort of threshold levels that are recommended. Are each of those legally enforceable?
No. Those are recommended values based on studies and tests by those agencies. The only legally enforceable limit is the OSHA PEL of 0.1 milligram per cubic meter.
Okay, and the rest are recommended based on research and experiences, and those are considered the safe and
best
levels. Yeah.
Those are recommended values for risk managers as best management practice.
Got it. You went through several examples. This attendee wants to know, in your experience, what's been the most common cause of a spill? What went wrong? And other than removing devices, how can we best prevent a spill?
Most commonly, I find that devices are broken, and it's thermometers, manometers that maybe aren't even broken, are just mishandled. A lot of things that contain mercury are open-ended, and they get spilled. So usually what gets wrong is something that contains mercury is just mishandled. The best way, other than getting rid of what you know you have, would be to maybe look into some other areas just to confirm that you don't have it. So maybe mechanical spaces, check thermostats. Even boiler plants have differential pressure meters that contain up to 30 pounds of mercury that people don't even know are on their facility until it's too late. We see that all the time. So I would say maybe we can even do a building material inspection just to confirm that all those materials are gone, and that can alleviate a lot of that.
Right, and it was apparent from your presentation that sometimes just kind of hiding it or putting it somewhere where there's less traffic doesn't always work. I mean, that manometer seemed to be in some sort of garage, and still there was an incident involved.
Right.
So you want to get rid of it if you can. Question here from Mark. What product in your experiences do you feel are more effective in mercury decontamination? Amalgams or sulfate-based materials?
I think amalgams, in my experience, are the most effective. Just the fact that it does amalgamize the mercury, it really prevents it from being volatile, and having that is the best way to prevent mercury vapor in the area, and I've just had success with it.
And you've used both products, both methods before?
I have.
Sulfate-based, yeah. Okay, next question. And we've got time for a couple more, so again, anyone who has one or two, throw them in, and we'll get back to you today, or if one comes up after the webinar, we can follow up with you as well. Next question here. Can we handle a mercury spill, especially a smaller one, on our own, or is it necessary to call a company like Triumvirate to come and clean it up?
A small spill is still a potential exposure. It can be done if you have the right tools and equipment, but it's common to think a small spill, you can grab a spill kit off the wall and clean it up quick and it's done. But as I said, a lot of times when something happens, mercury can find its way into areas where you don't expect it, and it'll remain there and remain volatile for a long time. So if something spilled in a common area, even if it is small, if you don't have the right meters and knowledge and real just safe work practices and cleanup, you can potentially have contamination that remains and that is still exposing people. So I would recommend calling a professional, even if it is a small amount of mercury, just to prevent any sort of exposure to the workers and the environment.
Great, that's good advice. And getting back to sort of the process here, a question here on what to do first. I guess it can be a pretty alarming thing. So what's the very first step that should be taken once a spill is observed? Do we make the call? Do we sort of quarantine the area? What do you recommend?
Yeah, the biggest thing is to isolate the area. Like I said, a big thing is cross-contamination. So if something falls and breaks, or you find mercury contamination on the ground, the first thing is to take a step back, leave it alone, isolate the area, and maybe even think of what just happened. How much mercury is contained in the device I just had, or how much potential contamination is there, as opposed to trying to act and maybe making the situation worse. Step back and maybe contact a professional.
Great. Okay, so it looks like we're winding down here with the questions. I got one here asking if a recording of the presentation will be available, and the answer is yes. We're going to send the recording and the slide deck that Ryan presented by tomorrow morning. So you will receive this, a link to each, so you can view this on demand and for your reference. So hopefully you weren't scrambling, jotting down notes the whole time, but you will get the materials. Let's see here. We've got, let's take one last question here, and this comes from Dan. What recommendations do you have to reduce the risk of further contamination once the spill occurs?
Minimize traffic and minimize air movement. If a spill were to occur in an area, a common area, definitely isolate it. Keep people from tracking it, and try to keep the mercury vapors contained in that one room, if possible. That'll definitely help prevent anybody outside of the area getting getting exposed, and limiting traffic is going to help prevent cross-contamination.
Right, and then you can set up your strategy, right, from cleaning up from there. You mentioned setting up the zones and grids to make sure that that doesn't happen even as the cleanup is in process.
Correct. It's a monitoring during the whole process,
right,
to find hot spots, and setting up a grid to show those levels really helps to illustrate where contamination occurred.
Excellent. All right, great. Well, Ryan, I think we'll start to wrap things up there. I think that was a great discussion on mercury and the hazards and ways to clean up and respond to mercury spills. Hopefully, it doesn't happen here to anyone on the call, but hopefully you're more prepared after listening to some of these points and the case studies. So, Ryan, I think we'll move on here. Do you have anything else to add before we close down for today?
Just thank everybody for attending, and let us know if you have any more questions. Thank you.
Perfect. All right. Well, that concludes the webinar today. Thank you, everyone, for your attention and for participating. Some great questions that came in. If any more come up, please get in contact with us. I'll be sending an email, as I said, shortly, and you can respond to that with your question. And that'll be that. So we'll send a short survey as well. Please let us know what you thought. Take care, and we'll see you next time. We have a webinar next week on the state of the EHS industry, presenting on some research that we've conducted with EHS professionals. So be on the lookout for that one. Thanks, everyone. Have a great day.